Introduction to History and Foundations of Machine Learning, and that is again on the background of research for long years. I want to mention this book from 2018. The title was The Digital and the Real World. But real world, you will see later on in the talk, does not only lead physical reality, but the world of real numbers. And real numbers is the world of analog computing. So analog computing in the following will play a crucial role. Then the books which I already mentioned yesterday, Artificial Intelligence, Limits of AI, Quantum Computing, and then, especially from the last year, this book on artificial intelligence of neuromorphic computing. That means brain-oriented computing will also be considered in the following. And then this philosophical handbook of artificial intelligence, also edited in the last year. Now, on this background, I will speak at first about history and foundations of machine learning. But then we will consider way outs of modern machine learning, alternatives with causal learning and neuromorphic learning, brain-oriented learning, and in the end, we will consider a perspective for machine learning and AI in the future. Now let's start a little bit with history of machine learning. And here I like to begin, as mainly in my talks, with this paper. Turing, amazing, 1936, 37, you know, the introduction, you mentioned it already in your conference, the introduction of the Turing machine. I will not go into the details here of the Turing machine again. I only for the following wanted to highlight the following aspect in the theoretical concept of Turing, namely the strict separation between memory and processor. And in the case of Turing, that is illustrated here, the memory by a tape which is divided into squares which can be printed by digit, and you know, all kind of information can be encoded by digits, and the tape on both sides is unlimited, and then that is the memory, and then the processor. The processor with commands and computational devices, such as in this case deleting or printing symbols, shifting the tape from left to right. Now, this concept turned out to be mathematically equivalent with other definitions of digital algorithms, and that following church thesis highlights the Turing concept until today as the representative definition of a digital algorithm. And Turing also introduced the concept of a universal Turing machine, and that means theoretically the machine is able to simulate all kinds of programs, and that is technically the concept of a general purpose digital computer. And the first one was built here not here, but at least in Germany, in Berlin, by Konrad Zuse in 1941. I underline that because this architecture here, the strict separation of memory and processor, is nowadays called the von Neumann architecture. But actually von Neumann historically is the second one, with the ENIAC in 1955 and 56. But that machine has historical importance, you know, that made possible the American atom bomb. Now, anyway, on this basic, in 1950, the definition of Turing of artificial intelligence with this famous Turing test, and that is a kind of simulation game. It requests that a machine, a Turing machine, for example, should be called intelligent if it can be not distinguished by its reactions and answers from a human by a human interrogator communicating with both man and machine hidden behind the wall. And now modern machine learning. Modern machine learning tries to simulate the brain, because the idea is the brain is an organ which is learning by sensors from the data. And this is a modern representation in medicine of our brain by PET pictures, positron emission tomography pictures, and you see excited simultaneously firing neurons are here colored in yellow and red in these patterns. And I like this picture because it underlines the state of the art today. The patterns, they are stuff for the neurobiologists. They are interacting what is going on, pattern emergence here in the brain. But on the other side, these different patterns are correlated with, and that is stuff of the psychologist, the cognitive scientist, is correlated with different cognitive states such as emotions, perception, thoughts, and consciousness. Now, anyway, on the micro level here, from a medical point of view, we can study the neurons here, which are interacting with other neurons by synaptic connections that is described here in more details. The cell body here of a neuron generates an electrical signal which is sent along the axon, and then in the end, in the axon tips, by the electrical signal, certain chemical substances are initiated, and they are poured in the gap between the axon tips and the dendrites of the next neuron. And these chemical substances dock at these dendrites, and then depending on the doses of the chemical substances, a new electrical signal is initiated in the following cell body, and that was measured by in the first time by two Nobel Prize winners of Great Britain from Cambridge, Hodgkin and Huxley, in the end of the 40s, beginning of the 15th, and they measured for the first time this rule here, summing up of a certain number of inputs of a neuron initiate this electrical signal. And that was also mathematized by them. They were physicians, no mathematicians. And that is mentioned here, summing up the inputs, signals, weighted by numbers, the weights, that means the neurochemical intensity, and then some bias, and this is the activation function here for the output, the excitation. Now, with that in mind, in this time period, the computer scientists and the neurobiologists, some neurobiologists, had the idea to understand the brain as a kind of computer. And that was the idea which came up by McCulloch and Pitts. McCulloch, American neuroscientist, and Pitts, a logician, and the neurons as logical units. That is here illustrated, as I mentioned before, summing up the inputs here, and then the sum here must be larger or equal to some threshold value here, theta, and then the activation function here, the neuron is firing, otherwise zero. And in that sense, the neuron should be considered as logical gates here, as I mentioned yesterday already. The end function neuron only fire when all the inputs are on, and the end or function neuron would fire if any of the inputs is on. And then the picture which I showed already yesterday, a survey on the classical logic, the Boolean algebra of gates, in a classical computer. But in the beginning of the 60s, the neurobiologists, physicians, and so on became more and more skeptical to this concept of the brain, and especially Walter Rosenblatt. And Rosenblatt was an American biophysicist, and he had the idea we must build a machine. We must build a machine of neural networks, not only modeling, such as Konrad Zuse and von Neumann built their digital computers. And that was, in the 60s, the perceptron, and the idea was the human visual perception with the visual cortex should be simulated by a hardware machine. And this plate here simulates the retina, technically are equipped with photo cells, and then it is fixed, connected with another plate which should simulate the visual cortex, and then also fixed but by random connections to what Rosenblatt calls association units. Here, fixed connection, but then between the association unit and the response unit, there should be variable connections with weights. That means here in that part, learning is possible. That was the idea. Schematically, that is a two-layered network. This is the input side here, and this is the output, and here is learning. And people were very optimistic in that time, now with the neural network in the 60s, but then all the hopes collapses by a famous result, mathematically rigorous proof by Marvin Minsky, papered Minsky in that time, the head of the first AI center at the MIT. And they proved that the perceptron is not able even to solve and simulate very simple problems. For example, here you remember yesterday in my talk, the XOR per gate. XOR, the exclusive OR, and this is a logical truth table here with the outputs. You know it's only true if there are different inputs. And why is that not possible to simulate it by a two-layered network? And because of the decision condition mathematically of a two-layered network. That is here. The input, the photocells, for example, in the perceptron, then the weights, some bias, step means the activation function, which I mentioned, and then the output. And from a mathematical point of view, that is a linear equation. And linear equation represents geometrically a straight line. And now we consider the problems we discussed already yesterday. If you consider here the distribution for the XOR truth values, then you cannot separate the zeros and the ones by only one straight line. That is simply here the reason for that problem. And here are pictures which you already showed yesterday with linear pattern formation. That's fine, but here it's only possible by a curve, and that means nonlinear pattern recognition. And now the solution for the XOR gate here. The gate had traditionally two inputs, A and B, and the output. And if you have a problem and it is not solvable, how can you solve the problem? You have a glance on the condition of the problems and try to overcome the conditions. The conditions were two-layered networks. Now, they introduce in that time a second or third layer here, intermediate layer, the so-called hidden layer. Hidden layer because it has no contact to the environment only to the input layer and the output layer. And that layer has two neurons, H hidden, therefore H1, H2, and then the connections here by these arrows with the synaptic interactions with these weights, and then you formulate the activation rule, and they are now nonlinear equations here, and then you must do that for the whole network. Here, that's the task. You start with the first layer with the two inputs, then the connection with the hidden layer with the nonlinear activation functions, and you need a connection with the output layer. Again, the two nonlinear equation connection with the hidden layer, and then the connection of the hidden layer with the output layer. Now, that is fine. Mathematical description and learning weights means you change the weights, the biases, and this is a selection of possible values for the weights and the bias, and you can prove and check that in this case the network is able, three-layered network, to solve this problem. Now, and that it seems to be so simple, but it opens the door with multi-layered network to modern machine learning. This is a survey on some simple architectures of neural networks with the nodes representing the neurons, the arrows, the synapses weighted by numbers, and then from neurobiology we know this rule which I mentioned before of Hodgkin and Huxley, and also it is sometimes called Hebb's rule. It is a linear rule, which means that summing up the inputs leads to the activation. And by that, you get a stream of signals which is led through the whole architecture here of the neural network. And that is triggered by learning algorithms. Learning algorithms, maybe yesterday we mentioned already the supervised learning. That means that you train the neural network, for example, a photo, colored pixels with colored pixels, they will be adjusted by changing the weights, and by that the system is trained with this pattern, and then it is able to perceive among a huge number of other perceived photos of persons, for example, this prototype. And then non-supervised learning means that the system is able to recognize by itself similarities of data, and by these criteria it is able to classify the whole data set. And reinforcement learning means that the system is able to solve a problem by itself with respect to rewards from outside. Imagine a child in a classroom which is corrected by a teacher, or deep learning only relates to the depth of the system. That means to the number of the layers. Now, that is fine, but now I want to underline that modern machine learning is not simulating the brain. That was only an inspiring idea in the engineering research, because I think even more important is the influence of physics, namely physics for modern AI. And that was highlighted in the last year by the Nobel Prizes in physics. Two physicists get the Nobel Prize in Physics for AI research, and one of them was John Hopfield. John Hopfield was actually a solid-state physicist. And what do solid-state physicists? They consider solid-state bodies, macroscopic bodies like a ferromagnet, for example, consisting of many atomic dipoles with arrows showing the two alternative states, up and down. And now the complex system in physics can be annealed to a certain critical point of temperature, the Curie point. And in that At that situation, then nearly all the dipoles are jumping in one direction. They enforce themselves, and we get regular pattern emerging from an irregular pattern characterized here by the total magnetization of the body. And that inspired Hockfield to translate it now in a context of a learning neural network, and only one-layered neural network instead of the atomic dipoles here. Now neurons with alternative states. Here black and white, a irregular pattern at first, and the physical phase transition is now translated into learning rules of neural networks, in the sense that they approximate a pre-trained regular pattern, such as here the shape of the letter A. And that can be generalized for multi-layered systems, which is illustrated here with 4 layers. I think the neocortex has 6 layers, and here in the technical example 4 layers, but very similar. The process here on the technical side, on the first layer, colored, different colored pixels are recognized, and they are connected as edges and corners, then as partial faces, and then the whole face. That is nice, but modern neural networks are of this kind. They are huge. And there are not only 4 and 6 layers, there are hundreds and thousands of layers in the industrial application nowadays of neural networks. And they consist of millions of neurons and billions of synaptic weights. And that is mathematically represented by a network function, depending here on the input, and theta means the distribution of the synaptic weights. And then the idea is to train this network function, and that means changing the synaptic weights from theta to theta star in order to approximate some target function here. Target function represents a certain pattern which should be recognized. And now, from a mathematical point of view, the crucial result of whole machine learning nowadays, and that is the universal approximation theorem. From a mathematical point, that's all. Mathematicians are no longer interested in machine learning, because this theorem gives a guarantee that for a target function, they must be continuous. But for every continuous target function, there is neural network which can approximate this target function. But as often in mathematics, that is a poor existence theorem. It is absolutely not constructive. It says nothing about the parameters which is necessary to find some appropriate neural network. You only know there must be some neural network. And another often mentioned critic is that this complex system is a black box. Nobody knows what is going on here in details in the net. But I must say, from a mathematical point of view, don't worry, because these kind of complex systems are well known in mathematics, in physics, since over 100 years. Because in thermodynamics, we consider complex systems of molecules. A liquid, for example, a gas, for example, consists of millions of interacting molecules. And the mathematics is well known. It was introduced by Boltzmann. There is a Boltzmann Street in Garching, and Gibbs, and so on. So the mathematical formalism is well known here, and that is explained a little bit here. With this formalism, you can describe the interactions of the molecules weighted now by energetic weights. You get certain energetic expressions to characterize several ordering molecules in the whole liquid. for example, and then by annealing or gradient descent, you can arrange certain equilibrium states in this complex physical systems. And now again the idea to translate this formalism into a cognitive system, and that means here that instead of the molecules you consider here neurons, these are the synaptic weights, the corresponding expression, and the phase transition in physics again correspond here to learning algorithm in this kind, statistical mechanics. These are stochastic learning algorithms which aim at, on the physical side, equilibrium states, and here the target function. And this formalism is connected nowadays, also applied in industry, for example, by VW. They use it for traffic optimization. The idea, there is a city and it's a street map, and then you want to optimize homogeneous traffic everywhere in the city. That's an optimal global solution, not only locally in some suburb. And these kind of systems are characterized by an energy landscape. You know that perhaps from physics, and you remember energy in the cognitive system is interpreted here by the neurons and the weights. And then the state of the system is illustrated here by a ball, and the ball is running up and down here, the landscape, and the solutions are characterized by the valley, the local minima, and of course you want to aim at the global minima. That means here the deepest valley, which should be connected with this optimal solution here. And that was introduced by Hinton. That was the other Nobel Prize winner in the last year, also physicist. And the machine, the neural network, was of course called after him. Here, the Boltzmann Street, it is the Boltzmann machine. Now, this technology, the same is applied in the chatbots. Nowadays, you know, we mentioned it yesterday already, ChatGPT by OpenAI, that's the American version, and it is also founded on the idea big data and applying the learning algorithm. And some people are horrified that they are nowadays passing all kinds of Turing tests in the university, at least at these tests are based on large language models. But again, from a mathematical point of view, I must say, don't worry, because have a look in the machine room of these algorithms, and you find, what do you find? The well-known algorithm we discussed for several times, the supervised learning. You must feed the whole system by a lot of documents. Then the reinforcement learning. You know that by practical interaction, the system is able to improve your answers with respect to rewards or critics by the user. That is the reinforcement learning. But on the basics, it's simple statistic. The system is calculating statistical expectation rules for letters and words which should be inserted in a context of a weighted network. So it is statistic, and therefore I like still to call it a stochastic parrot, because it's only simulated by this big data stuff, human behavior. You know, there is a strong competitor nowadays in China, DeepSeek. Actually, it has some advantages because it is less expensive. You do not need this very expensive NVIDIA chips by OpenAI and so, and it needs less energy. That's also interesting. We could also discuss now the machine room of DeepSeek, here with the training pipeline of DeepSeek. I will not go in these details, but I want to highlight at least one point. That is clever engineering. The mathematics is the same. It is clever engineering here, and there are certain components, and there is one component which was invented here in Europe, in China, applied. Here in Europe, in France. France and Europe is leading in AI, I must say that as a German. And here by Mistral, the leading AI startup in France. And they, many years ago, they introduced here this component. It's called mixture of experts. And that's very clever from an intuitive point of view. If you have, for example, a mathematical problem, the beginner is calculating widely in all directions. That use a lot of energy. But the expert is saying, oh, keep calm and let it first a meta reflection. What kind of problem is it? And then the next point is, which are the tools which can be used to follow this strategy? And so it needs not so much energy. Now, nowadays, this kind of machine learning is not only applied in language, large language models, but later on the questions, because to be in time. And large language models, and here this is an application now in car industry, automotive cars based on large language, not language, but motor data models. That is exemplified here with a simple toy car with two wheels, and here the sensors, and equipped with a neural network. And that system, even real cars nowadays, can be trained by big data in order to avoid traffic accidents in the future. And then there are other possible big data applications. For example, visual data for simulate human visualization, or the motor equipment, and so on. And that is coordinated nowadays in robotics. That is a picture from an exhibition recently in Japan, from a robot that is state of the art. This smart girl here. And if you have a look again in the machine room, you find all the well-known learning algorithms, supervised, unsupervised learning, and especially reinforcement learning. Now, is that all? Is that human intelligence? Big data and then learning algorithms? No, we know that, because human intelligence is able, with very few data, to have ingenious ideas, and that leads to the concept of causal learning. And that goes back philosophically to this famous debate in the midst of the 18th century between David Hume and Immanuel Kant. And to make a long story short, modern machine learning is completely on the line of David Hume. That means big data and then finding some correlations. For example, these examples which were discussed in that time, there is lightning, and then after some time we have the sensation of thunder. And if you hear that for several times, again and again, then you assume a correlation. And then the critic of Hume was, that's all. And he was criticizing the metaphysical concepts in that time, the beliefs that there are laws which are created by God or by nature. No, he said, there are only these correlations of our sensation. And then Kant. And Kant said, with that concept, you will never found modern physics. That was Newtonian physics. What you need is, in modern language, hypothesis. You need what he called a categorical framework. You must assume that. But then he agreed to Hume and said they are not achieved by God, but they are the categorical framework in our mind. And now that is now illustrated here from a modern point of view. There are at first the statistical approach of machine learning. We start with finite samples, and then we try to derive by probabilistic assumptions some probabilistic model based on certain correlations of these data examples. And from this probabilistic model we can derive, and that is called statistical reasoning, expectation values for possible events. That's a statistical machine learning approach. And now causal learning. Causal learning says, okay, there may be some data, some events, but then you need a causal, what Kant called the causal categories. We need some hypothesis, and then we can derive causal model, and then it is possible to give this amazing prediction. In the 18th century, that was the situation of Newton. And Newton did not find the gravitational law by observing in a stupid way. You know, he was the son of a farmer, and then he flight from London to, there was a pandemics in London, then he flight to the farm of his mother. She was still alive, and was observing in a stupid way the apples falling from the tree in this farmer's garden. That is the propaganda of Voltaire to support the empirism. No. The ingenious idea of Newton was there are already laws, namely Kepler's laws, and we connect Kepler's law with this ingenious assumption, the three axioms of mechanics, especially the second axiom, that is the axiom of force. And that says, generally speaking, every change, mechanical change in the world, for example, velocity changed by acceleration, has a cause, and the cause is force. Yeah, that's a force law. And that was combined, and then he get his gravitational theory, and by that, this causal model, he could explain and predict the events in this fascinating way, especially in that time. Now, this is a simple example of a causal model. Here, the events are represented by random variables, and the arrows indicate the causal interaction. This is a cause for event x1, but is also a cause for x2, and so on. And that can be characterized here by causal laws. That means functional laws, nothing else. Here, the input, the cause, and some independent noise vector, and then that the effects. It's exactly describe this situation here. Now, the idea is, how can we recognize these causal structures in the distribution of observations? And in this example that is illustrated here, mathematically, the data distribution is described by this probabilistic density, and then you can start to ask for the dependence and independence of these events, and that is probabilistically here described by conditioned probabilities. For example, x4, this event is conditioned by x2, x3. That means x2 X3 are interpreted as reason for this effect. So, and that is done here for all these factors. So the idea of pattern recognition of causal structure in the wildly distributed data means mathematically factorization. Factorization here of the density function, that is a so-called Markov property. And by the way, here these symbols were introduced by Pearl, a philosopher and a computer scientist in the US. He wanted to found a kind of logic of logical thinking, but that is only another terminology and symbols for this probabilistic situation. I will not go on in these details. So the general task is you start with a sample from probabilistic data distribution of random variables, and then the task is to find this causal model here, structure, and in the end you can read out this causal graph in this simple case. Now the question is, can that be done by a machine? Can that be done by a machine? And the answer is, in general, we do not know. But what we know and what we can prove nowadays is that for restricted domains, and these domains, for example, in medicine, application to certain data sets, they are characterized by certain constraints. The constraint can, for example, concern the kind of a functional assignment. Are they linear? Are they nonlinear? Or the kind of noise? Is it Gaussian or non-Gaussian? Whatsoever. And then you can precisely, a priori, philosophical speaking, prove that this kind of a domain must have some causal structure. And that can, of course, given to a machine. By the way, that is done in Tübingen at the Max Planck Institute. They are working on that topic. But nevertheless, it's still in infancy. I highlighted that here because it proved that in principle, causal thinking is not a reservation for humans. It can be done by machines. Now, all that, what I discussed until now, is simulated by a von Neumann machine. That's our computer, by digital computer. And now I come to a very important point, because with this digital computing, we are running in serious problems in the future. Because this is the CPU. Nowadays, GPU, graphic, but it doesn't matter. It's only acceleration. The structure is the architecture. This is the same which I highlighted in the beginning with the Turing concept, the strict separation of memory and of processor. And then the increasing data nowadays must be pressed through this architecture. And that needs a lot of energy, and that needs a lot of time. And so this digital computing is nowadays seriously connected with our energy problem on Earth. And quite different to the evolution and human brains. Human brains only need 20 watts. Unbelievable for all these abilities of our brains. And the main reason, one of the main reasons is there is no strict separation of processor and memory. We use here in the living brain networks, and the living synapse in the brain integrates both functions, processor and memory. It can both. And there is not only one synapse, there are billions of them. So in the living brain, there is no danger of a von Neumann bottleneck. So neural networks are still used, in machine learning, but here they are only simulated on the digital computer. So that's no advantage for our energy problem. And the question arises, is it possible to build a neural network? Again, in the tradition of Rosenblatt, is it possible to do that in hardware? And then we can say in American way, yes, we can. Because in the beginning of the 70s, Leon Schur, that was or is an engineer, electrical engineer, and a computer scientist from UC Berkeley, by the way, also a distinguished professor here in our computing electrical technical faculty. He came up as a young man with the idea, theoretical idea, to find a kind of transistor which is able to integrate processor and memory. He calls that memristor. That's a combination of memory and resistance, and that would be a nice technical candidate to simulate the synapse, you remember. And since 2000, I worked with him, and we wrote books and articles, but that were concerned to mathematical modeling, electrotechnical neural networks, which were able to simulate the neurobiological interaction which were described by Hodgkin and Huxley, and then the ideas, the synapses in electrotechnology simulated by these memristors. And that is illustrated here for one layer here. This in the graph, the illustration here in this matrix, and here the inputs, that means voltage, and here are the symbols of these memristors. They are simulating the synapses. And what are they doing? They realize energy efficient parallel analog in memory computation mathematically here in the matrix as vector matrix products. And the outcome here, the output, are current. And perhaps you remember from your school physics, you learned that voltage is proportional to current. That is a famous Ohm's law. By the way, again, we should here be in Munich, and in the city you find the memorial of Ohm, here in Munich, a physicist in the beginning of the 19th century. Now, that is the law here, and here is a proportional constant, and that is resistance, measured in ohm as units. And if you consider here it in the coordinate system with voltage and current, then that's again a linear law. You get a straight line. But the idea is we want to have a unit with memory. And so the question is, are there materials with these features? Yes, there are. Titanium dioxide, for example. A strange name, but it's not very exciting because you can find this substance in your sun cream. It is no rare material, not very expensive, but if you treat it with charge, for example, then the molecular structure is changing, and in that way there is a relation to past states, and in that sense there is a kind of memory. And mathematically that is here described by the proportional factor, which depend on the charge, and by that you get nonlinear equation, and therefore the illustration here in the coordinate system is this curve here, the so-called curve of hysteresis, and that is a signature for all kind of materials with this memorial feature. There are today a lot of other materials. I mentioned that because that was the reason, because I only could come yesterday, because on Monday I was on the annual meeting of the advisory board of our federal ministry concerning the future cluster neuromorphic systems AI. And that is, they are working in RWTH Aachen, the other great technical university in Munich, and they are not only considering our modeling, but they are building it. Building with the industry, neighbored also Belgium and Netherlands, building especially concerned with the application of this kind of materials. Now, in that context and other research groups also, the idea came up to improve it, namely instead of electrons, to consider photons. Photons, photonic-based neuromorphic computers, and because that would have a lot of advantages. Photons with laser light in a silicon environment, because that would be much faster with nanoseconds of photons instead of milliseconds of electrons. And it would be more energetically efficient in the sense that these memristive systems have 75 watts only. And that's very close. You remember my remark concerning the living brain with 20 to 25 watt. And I like to call that, here that is an illustration, of course, a brain of light, because you are calculating now with the photons. And my personal idea is to connect it with quantum computing. Because if you are considering photons, yesterday we discussed about that, these are nice candidates of quantum systems. And you know the advantages from yesterday, quantum computing. There is entanglement and there is a superposition. Perhaps some of you remember, I think 20 or 30 years ago, Roger Penrose, also now a Nobel Prize winner, famous mathematician from Oxford, he came up with the idea to model mathematically our brain, not in the Hodgkin-Huxley way, also British, now from Cambridge, very interesting. And, and he suggested to model it, the brain activities, by quantum mechanics, because this idea was, entanglements, that's nice to connect locations, different locations in the brain, superposition, things like that. And he was heavily criticized by the neurobiologists, by reasons, neurobiological reasons I will not go in the detail, and so it was a little bit forgotten. But here, my idea was, 2 years ago, I had a discussion in Oxford about that, and I suggested, under the impression of the memristive systems, I suggested to apply the quantum mechanical formalism not to the living brain in order to understand the brain, but to, in the engineering sense, to apply it to these memristive systems here, with the feature of entanglement, superposition, and so on, to test what are the possibilities of this technical brain. But that is nice from an energetical point of view, and you understood, I hope so, the advantages of concerning the energy problem of these neuromorphic system. But now, in the end of my talk, I come to a crucial point. I like it, because it leads us back to the foundations of digital computing. And so I started with Turing, and I will end with him, because in the paper of Turing, and that is not well aware by our computer scientists and AI researchers nowadays, just from the beginning, this approach is connected with strict limits. That is the undecidable problem, the so-called halting problem of Turing. It says, some of you will know that, but it says, roughly speaking, that it is not possible to decide in general for arbitrary algorithm with arbitrary inputs that this algorithm will stop, that means a Turing machine, after finite time. It is absolutely not possible. I will not go why. It's actually a simple argument. By him, it is a logical argument. But anyway, it is in principle not logic, not possible. It does not depend on technology. Perhaps in 100 years we go, no, never. But the restriction is digital computing here. And that turned out, it's not only a logical problem, to be mathematically equivalent with mathematical problems. 1970, Matyashevik in Leningrad came up with this proof. For example, the famous Hilbert's tensor problem concerning the Diophantic equation solution with digits, or Hilbert's Nullstellen Satz, which is a generalization of the famous fundamental theorem of algebra of Gauss, and things like that. They are, in that sense, in principle, not solvable. But then, 20 years later, on the basis of that, is the Gödel, the great Gödel. Because in 1931, you remember the halting problem was in 1936, 37. In 31, Gödel came up with a theorem: there exist definable but undecidable sets over the digits, and such as the universal approximation theorem. That is the basis, the simple sentence of our digital world, of our computers, of our machine learning, all that from a mathematical point of view. This simple theorem of Gödel, because it sets forever the limits of digital computing. I think that is amazing. And now, 20 years later, Alfred Tarski, here on the left, that's Turing. Picture, I think, in the end of the 20s. And Tarski came up with the proof: every definable set over the real numbers is decidable over the real numbers. And that means analog computing with real numbers, neuromorphic computers, may overcome the limits of digital computing. All these problems which I mentioned. I have today not the time to illustrate that with a practical application, namely in medicine, imaging, medical imaging. There can you also demonstrate that there are problems which with the digital computers, which are used in the faculties of medicine everywhere, cannot be solved in principle with this digital framework. I will not go on that, but come to my last folio here, the innovation of machine learning. On the one side, this great hope: when do machines take over? But on the other side, the limits, which I mentioned here in several examples during my talk. Now, as far as we know today, there are no absolute, unconditioned limits of computational reasoning. And the logical, mathematical, and technical, practical limits depend on conditions which could be overcome. That was sometimes overseen in the philosophical discussions. They said, oh, Gödel, Turing, wow, that is the limit of formal thinking. Not, because it depends on the strict conditions of digital computing, which I mentioned. So these conditions, as far as we know today, can be overcome. The limits of digital by analog computing, statistics, causal computing, then quantum computing concerning the velocity. But it does not only depend on logic or computer science or mathematics, it also depends on the different hardware. We know silicon, for example, titanium dioxide I mentioned, and other materials, and the electrons, the photons. You remember the difference of photonic neuromorphic and membristic photomorphic approaches. Then the different kinds of energy efficiency and the size of the large language model. So the crucial question is, in the end, are we on the way to artificial general intelligence, AGI? I must say, from my point of view, we don't know. Maybe the future is open, maybe, but it needs other approaches. But what we know nowadays is that the long-term breakthroughs of innovation in AI have been on the borderline of logic, mathematics, computer science, physics, neurobiology, and material science and engineering science. Logic and mathematics is not sufficient. And neurobiology, that was the hope of Rosenblatt, is also not sufficient. It needs physics and it needs material and engineering science. What does that mean in the end for philosophy of science? I think that is a great challenge now, because in order to get the great breakthroughs for the future, you must on the one side be aware of the philosophical foundation, and that means actually also the philosophical tradition. For example, here I discussed Hume and Kant. But on the other side, for philosophy of science, it needs a coordination here in our seminars of these different disciplines. And that should be the task of the philosophy of science. And I hope for the future here with the summer school, we will do exactly this job. I thank you for your attention.